Welcome to GBL301, Application Architecture as Code. I originally gave this talk in German, so I'm now re-recording it in English to make it available to a wider audience. I'm a senior principal evangelist at AWS working on serverless automation. And in this session, I want to take a fresh look at cloud automation, challenge the notion of infrastructure as code a tiny bit, and outline a vision for architecture as code. And when we think about automation, usually a picture like this comes to mind. And that reminds us that automation isn't exactly a new idea. Right? Ford revolutionized the automotive industry by building the Model T on an assembly line much more efficiently than it could have been done by hand. And that often leads to the conception that automation is fundamentally about efficiency. And although the assembly line was a great invention, we need to keep in mind that that was 100 years ago. So in the cloud, automation plays a much more diverse role. And the first aspect of that is speed. In a world where we have ever shorter product release cycles and faster innovation, moving quickly is critical. And thanks to automation, you can do things fast and at high quality. Automation is repeatable. The next time something runs, it will run exactly the same time as the 999 times before them. And that gives teams confidence. And that's important because if teams lack confidence, they'll hesitate, which slows them down, or they will not fix items because they're afraid that something else might break. More importantly, even, automation allows teams to work entirely differently. When we provision virtual machines manually, we would care for them like we care for pets. We would try to keep them alive and feed and maintain them as long as we can. With automation, you can dispose of and recreate resources as many times as you like. And that gives you great advantages because you always have a fresh and clean image in the resources. And last, everything that's automated can be measured, and what can be measured can also be improved. So we should remind ourselves that cloud automation isn't just about efficiency. It's not just about reducing toil, but it's about working entirely differently. With automation playing such an important role in the cloud, we could go as far as saying that if you took automation away from the cloud, you might end up with not much more than a traditional data center. And we have very nice data centers at AWS, but the whole point of going to the cloud is to get rid of data centers, not to get yet another one. So looking at the history of automation, the term that we commonly use is IAC, infrastructure as code. And that has to do with the origins of cloud automation. A traditional organizational model, it has the developers writing application code, and then that code is handed over to the infrastructure and operation teams to run it. And the development teams, they focus on the functionality, whereas the operation teams, they will assure the non-functional requirements, such as performance and uptime. And for that, they would provision infrastructure and they would use scripts to do that. And that means that automation was the domain of the infrastructure teams. That explains why we use document-oriented languages like YAML file. Right? Developers love complex, expressive languages for their business domains. Right? They love to have object-oriented constructs like inheritance and polymorphism and type systems and all these other nifty things. But the operations teams, they don't have that much complexity, so they would prefer simpler languages and strings and integers. Developers would use agile methods and test-driven development and do automated refactorings in your IDEs, versus the operation team's probably happy to use a text editor. So respectively, each team had the right tools for their purpose, and everybody was reasonably happy with the role they played and the tools that they use. Until sometime late in 2014, when everything changed. That was when AWS released Lambda. And Lambda really redefined what a modern cloud application looks like. Now with serverless, there is no infrastructure to manage. Those applications also tend to be more fine-grained. So how the functions are connected now matters a lot more. At the same time, automation languages also evolve to become more object-oriented, right? And on top of all this, we have serverless integration services like EventBridge that provide application-level functionality, like event routing or event filtering or transformation. So suddenly the neat picture from the previous slide was no longer adequate. And what we learn is that cloud automation doesn't live in a vacuum. It follows the application architecture. When cloud applications evolve to become more fine-grained and independent from the underlying infrastructure, the cloud automation also needs to evolve and go beyond just managing infrastructure. And to better understand this shift, we can decompose cloud application. The most well-known purpose of automation is to provision infrastructure. And the simple example I use here, right? You have two VMs, then you have a load balancer, you have an API gateway in front of that. But actually, just on their own, these resources that you provision, they don't do much. You need to deploy some applications or some images on top, and still you just have some disconnected resources. You need to connect them. You need to compose them into a working application. And last but not least, you probably make some configurations like which application talks to a primary or a secondary database, or you might have different log levels. So cloud automation actually does quite a bit, and that breaks down into these four distinct categories. Now, having this model allows us to better understand how the shift to serverless application impacts cloud automation. Serverless does infrastructure management for you, and deployment has become extremely simple. So the focus really shifts to composition and configuration. The composition is what connects these loosely coupled components into a working application. And it defines many of the essential properties of a serverless application, like its granularity, how big or small your functions are, and the dependencies between them. Many of these connections will use services like Amazon SQS or SNS or EventBridge that you configure then to filter and route messages between your serverless components. And the traditional IAC tools, as the name hinted, they actually focus more on the bottom half of this picture than on the top half. And we can see the issue with that by using a simple example. So let's assume you want to trigger a workflow whenever your data in your database changes, right? It's a very common use case, and it's well supported by AWS's serverless services. And in this high-level architecture, you would draw a diagram like this, right? The data from left to right. Now, the implementation on AWS would use DynamoDB, a serverless NoSQL database, and AWS step functions, right? The serverless orchestration and workflow tool. But the connection between the two, that would be done via EventBridge Pipes that was released at reInvent 2022. And Pipes can fetch the data from the DynamoDB stream. It can filter and transform these events, and then based on these events, it can trigger step functions workflows. But this picture looks a tiny bit different than the picture on the top, and that is because EventBridge Pipes has to pull the data. So this implementation shows the control flow, versus the picture on the top much more shows the data flow. Now, the implementation in automation languages follows the implementation, and that's whether you use a more traditional sort of CloudFormation style or whether you use an object-oriented CDK style, right? You can see here that you configure EventBridge Pipes, you configure a source and a target, but the way you do that is by providing a string. You provide the ARN of the respective source or the target. So what we notice is two things, right? That I first need to translate my architecture into the implementation, and then I need to code to that implementation in my automation tool. And also we see that the composition, right, the element that was so important to us, that's not really benefiting from the object-oriented library and the type system, that is really still represented by a string. And to say that in a bit more punchy fashion, we can use words by Kevlin Henney, who says that these things are stringly typed. Composition here is stringly typed. It's not actually strongly typed the way we would like it. To just quickly recap what CDK can do for us here, we should notice that CDK is an open source object-oriented library that you can use with general purpose programming languages, right? So it's easier to build higher level constructs, and because of that, you can more easily do things like set up a VPC, set up some EC2 instances, and even have complex constructs like a load balanced Fargate server. That makes you much more efficient because this little example alone would translate into about 450 lines of cloud formation code. Now, because we have a general purpose programming language, we get IDE support with helps and auto suggest, and you can do this across 6 different programming languages that are supported by CDK. So this is a big step ahead. And the nice thing about this is that because it's open source and because it's object oriented, the community can create higher level constructs. We call these level 2 and level 3 constructs. And in fact, the community is building a L2 construct for event bridge pipes, and that actually uses a type for the source and the target. You can see it here. There's the iPipe source as a type. And as you would expect, the DynamoDB stream source implements that type. So that is quite nice. This is strongly typed. This is no longer stringly typed. Now, using the type system is a great step ahead, but it's only part of the picture. When we look at traditional automation languages, right, when we focus on provisioning infrastructures, those resources were generally arranged in a hierarchy. Like an EC2 instance is part of an autoscaling group, and that sits inside a VPC, and that sits again in an availability zone. So it seemed natural for these languages to use the same model of a resource hierarchy. But when we look at modern serverless applications, they are fine-grained and they're event-driven, so they're much more interested in the data flow and the control flow between these components. And both of these models are useful, but in different contexts. If I mostly look at infrastructure like virtual machines, the hierarchy will be a good meta model to use. If I'm building fine-grained event-driven applications like I would do in a serverless context, then I'm much more interested in the topology and the dependencies between my components. And this is another major part of the shift in the automation languages. So if we try our example again, and we sort of want to do this in a 2020 style of programming, right? We have object-oriented languages, fluent APIs, architecture patterns like pipes and filters, and we apply that to our previous example. Then we should be able to express this using a nice programming model and using patterns like these enterprise integration patterns. So perhaps I want to split the records that come from the DynamoDB, and then I want to enrich them with additional data before I pass them to the step functions workflow. Now, how awesome would it be if the automation code could look exactly like this expressive high-level architecture where you define a source, you define several logical filters, and then you define a target in a nice strongly typed and fluent API. And now that is exactly what I am working on. And the code that you see here reflects this architecture very well. Right? The relationship has changed. The code is no longer based on the service implementation. The code is now based on the high-level architecture. And what I can do to translate this into the actual implementation, I can do that automatically. I can use something that's called a cloud compiler. And this is actually, it's a prototype, but this is running CDK code. This will underneath provision event bridge pipes. It will have an express workflow calling Lambda function for this logical transformation. So this actually knows how to map my more architecture-oriented specification to the correct services and the correct implementation. So if you want to make this more pronounced, this change is that the traditional model makes us code to the implementation, right? It makes us translate first from our architecture to implementation, and then again, it makes us sort of manually translate that into the automation languages. By using a high level of abstraction and a different composition model, by using this application architecture or this application topology, this pipes and filters, this fluent API, I have a very direct mapping from the way I think about my architecture to the way I code the automation. And then I can use automatic translation, right? We might call this a cloud compiler, to then deal with all the nuances and the push versus pull and all these kind of things for me. And this is actually a model that's much better suited to fine-grained serverless applications. So what we have achieved is, right, we now program our cloud automation in a domain model for application topology. We use a domain vocabulary of connections and patterns like splitters and enrichers. And that is really a long way from the traditional automation scripts that were mostly there to save us from having to perform manual steps. The automation is no longer it's no longer an afterthought to save manual labor, but becomes an integral part on how we think about applications in the cloud and how we develop software in the cloud. Now, if we look at this domain model a little bit more closely, we find that the runtime characteristics of these distributed asynchronous applications, they very much depend on the control flow. So let's take an event bridge bus as an example. So unlike pipes, a bus uses a push model. So that's a great match for sources like SNS. That processes events at the arrival rate that they come out from SNS. And in my little pattern language here, I denote that by the little nose. The nose denotes what's the active element, what drives. In this case, SNS drives the events through the event bridge bus to a destination like SQS. But that runtime behavior can change quite a lot depending on what the target is. So one target type supported by event bridge buses are API destinations, right? It calls an HTTP endpoint. Now, if you were to call that endpoint at the arrival rate of the events that are coming in, that would no longer be called an integration, that would be called a denial of service attack. So what you need is a rate limiter. You need something that calls the API at a prescribed rate, but that changes the little nose, right? This thing now has control, is the active thread, so to speak, at a certain rate of API invocation. So now you have a little bit of an issue. You have two noses facing each other, but luckily there is help for this case because there's an element that has two little nooks, and that is called a queue. A queue decouples control flow. It can take events at whatever the arrival rate is, and it can provide those events to the downstream components by whatever rate they fetch it with. So now we have a much more expressive way to explain the runtime behavior and how that changes with the targets. Funnily, in automation language, right, the only change here really would be the string of the destination, and it wouldn't really represent this huge change in the control flow from a pure push model to a queue and a push and a pull model. Yeah, the only difference we would see there is a string. So what we find is that we really don't have quite yet the language. Like, this difference should also be expressed in our domain model, not just like with little noses and nooks, but really as types in our type system. And we don't really have that vocabulary yet, but the good news is those are the things I'm working on when I talk about serverless automation and application architecture as code. So to take a small breather and to zoom out a bit, when we talk about modern cloud automation languages, we can really classify them along 3 different dimensions. Right? The one is the different language styles we mentioned, right? We have document-oriented things, like CloudFormation. We have object-oriented frameworks like CDK. And then we also have functional language, like, for example, Q, and some others are going that route. Then we also discuss a different composition model, right? We can either compose based on hierarchy, sort of nesting things, or we can compose them more along the topology, more at the control flow. And last, there's also quite a bit of discussion going on right now whether you should really have separate application code and automation code, right? If they use the same language, if you can write both in like Python or Java or TypeScript, and they're both object-oriented, right? The natural question should be, why does this have to be 2 different things? Couldn't I derive my infrastructure from my application code? And the keyword there is IFC, infrastructure from code. And just to reveal where I stand on this is, I like object-oriented languages because I like type systems and the support that it gives to the developer, and the IDE things like refactorings and auto-completion and underlines if your types don't match. So I like to have those capabilities. For fine-grained event-driven serverless applications, I feel that the topology is a much better match than the hierarchy, but I still like to be explicit about it because my topology really defines important runtime characteristics, like how well does my application scale under load, or how does it back off if I'll overload my system. I would like to make that explicit, and I would like to have the description of that topology be different from the functionality that I code in my application. So if you use this as a sort of meta model of what we're talking about, you can sort of map your position, and in the picture you see where I would stand on this. So what we really achieved, and what I hope I was able to convince you of a little bit, is that when we build modern cloud applications, we should really rethink the term infrastructure as code. And instead we should focus on application architecture and express that application architecture in actual code and perhaps not in a YAML file. So if you like this style of thinking and digging in some of these topics around cloud and automation, I like to write books about architecture, cloud, and platforms. And here's actually a QR code to a blog post that expands this topic a little bit more. Thank you very much.